Hello everyone. So this is my next session on events for System Verilog for verification. So events were also present in Verilog. But in this session we will understand how System Verilog enhances event handling as compared to Verilog and how we can use it effectively in our verification environment. So let's start it. So this is what we are going to cover in this video. We will start with an introduction to events, understanding what they are and why they are useful in simulation. Then we will move to triggering and waiting of events, a very important concept to understand events. Next, we will see few examples for usage of events in System Verilog test benches. We will also discuss the merging of events, few event operations, and the wait order construct, a very useful synchronization tool. Finally, we will wrap up with an assignment to test your understanding. So an event is a user-defined signal used for synchronization between two or more concurrently running processes or threads. So you can think of it like a handshake mechanism. Here one thread triggers the event and another thread waits for the trigger. You can declare an event by using this keyword event and then the event name. And to trigger the event, Verilog provides two operators. These two operators, the first one is an immediate trigger, while the second one is a non-blocking trigger. And to wait for an event to be triggered, you can either use the operator or you can use the dot triggered property with a wait construct. So we will understand all these operators in further slides. So you just need to know that these are the fundamental building blocks which we use for inter-process communication in verification environments. So now let's understand how events are triggered and waited upon in System Verilog. So if you for triggering, if you use this operator, so it will immediately unblocks all the processes that are waiting on it. So this is considered a blocking trigger and it occurs in the active region of simulation. So next we have this operator and this is the non-blocking trigger, means it executes in the non-blocking region. So in System Verilog, event is kept in a triggered state for the entire simulation timestamp. What does it mean? It means if multiple processes are waiting on that event, they can all catch it within the timestamp. But in Verilog, all the events are instantaneous. Means as soon as you trigger it, the event is considered triggered only for that precise simulation delta. Say if any process is not already waiting at that exact moment, then it might miss the event. So System Verilog improves over Verilog by making named event triggers active for the whole timestamp. So waiting of event using either or using wait construct, it also happens in the active region. Additionally, each event in the System Verilog has a built-in dot triggered property. So what is this dot triggered property? This is a Boolean flag and it returns true if the event was triggered in the current timestamp. So this is a quick example for this. So, for example, you are using this event, you are checking in a condition event dot triggered property, and if it is true, then doing something, you can add the else part also. So this lets you check and respond to an event conditionally within the same timestamp. Now let's take a look at few examples to understand how events work in simulation. So in this example, firstly we are declaring an event E. Then we have defined two initial blocks. In the first initial block, we are triggering the event using this operator. In the second initial block, we are trying to wait for the event using operator. So the main point here is both initial blocks starts at same simulation time, that is time 0. So the event is also triggered at time 0 and the waiting process also starts at the same time. So point here is cannot detect events that are triggered in the exact same time step unless the process was already waiting. Since both triggering and waiting happen concurrently at time 0, so at the rate would miss it and the process would still be blocked. So the output here is at the 0 timestamp we get triggering the event, at the 0 timestamp we get waiting for the event using at the rate. But since at the rate cannot detect the triggering of event which happened in the same timestamp, so this message would never get printed. So this is another example. Here the event E is again triggered using this operator. In the another initial block, we are using wait construct instead of at the rate operator. So here also in both the initial blocks, triggering and waiting is happening at the same timestamp. So unlike the previous example, this time the wait construct is able to detect that the event has been triggered in the same timestamp. So as a result, the process waiting on the event gets unblocked, and this time we are able to see this statement also in the output. So in the output, like at the timestamp 0, we see triggering the event, at the timestamp 0, waiting for the event using wait, and since wait is able to detect the trigger, so that's why at timestamp 0 we can see event is triggered using wait. So this example clearly explains the difference between at the rate and wait. So at the rate operator can miss the event if it is triggered at the same timestamp. So process would be executed only if it is already waiting before the event happens. So that's why at the rate is also called as event based. But in case of wait, it continuously checks the condition and resumes when it evaluates to true. And it doesn't need a signal edge. Condition may already be true in this case, in the case of wait construct. So that's why wait is also called as level sensitive. So this is another example, and in this example we are again using at the rate operator to wait for the event. So the only difference in this example is the waiting process starts at time 0 while the triggering is delayed by 10 time units. So this sequencing ensures that the at the rate operator is already active and monitoring the event when it is triggered at the 10 timestamp. So because of this, at the rate successfully detects the event trigger and the waiting process gets unblocked. And this statement would also get executed. So we can see clearly in this output, at the 0 timestamp, we can see waiting for the event using at the rate. Then at the 10 timestamp, triggering the event happens. And since at the rate can detect the trigger, so at the 10 timestamp, we can see event is triggered using at the rate. And this behavior is consistent for both at the rate and wait constructs. So if waiting starts before the event is triggered, in that case both at the rate and wait both can detect the event correctly. So this example is exact opposite of what we saw in the previous slide. So here we have declared an event E and it is triggered immediately at time 0, but the waiting process gets delayed by 10 time units. This means the at the rate operator begins waiting for the event after the event has already been triggered. And that's why it would completely miss the trigger. And because of this waiting process remains blocked and the final display statement would never execute. So the output confirms this behavior. At the 0 timestamp, triggering the event happens. At the 10 timestamp, waiting for the event using at the rate starts. But since at the rate cannot detect the trigger, so this statement would never print. So this behavior is same whether you use at the rate or wait. Means if the waiting process starts after the event trigger, in that case the event is missed entirely. Now again we are using the same scenario where both the trigger and waiting for an event occur at the same simulation time, that is time 0. Now the difference here is the event is triggered using this operator, and that is the non-blocking event trigger. So now what happens in this case? Because this operator works in the non-blocking region, while the @ operator works in the active region. So because of this scheduling order, the wait process is able to see the event trigger even though they happen in the same timestamp. So that is why all the three statements, triggering, waiting, and confirming the trigger, they execute successfully at time 0. So this output makes it very clear. So whenever you want to safely trigger an event and let processes detect it at the same time, you can use the non-blocking event trigger instead of blocking trigger. So this is another important concept in System Verilog events, that is merging of events. So let's say you have two event variables, event 1 and event 2, and if you assign one to the other like this, then both of them now refer to the same event, and this is called merging. So once you are done with merging, then triggering event 2 is effectively the same as triggering event 1. Or we can say that event 1 will also be triggered at the same time when event 2 triggers due to merging. So let's understand this with the help of this example. Here in this at timestamp 10, we are merging E2 and E1. Then at timestamp 20, E2 is triggered. And at timestamp 30, we mention E1 is triggered. But since because of merge, E1 is also considered to be triggered at the same timestamp when E2 triggers. So here we have two wait statements, first for E1 and another is for E2. So both wait statements are unblocked at time 20, even though E1 was supposed to be triggered at timestamp 30. But because of merging, both of them now triggers at timestamp 20. So that's why both wait statement gets unblocked at timestamp 20. So this output clearly shows this. So this feature can be extremely useful when you coordinate multiple processes through a shared event. Next, there are a lot of other operations which you can perform with System Verilog events. For example, you can reset an event variable by assigning it the value null. For example, event equals to null. Second, to wait for any one of the several events, you can use the OR operator with the @ operator. For example, in this case, process waits for either E1 or E2 to trigger. Next, if event identifier is null, then the triggered property for that event evaluates to false. So this is useful to avoid unwanted triggers in uninitialized events. Next, comparison operators like all this, they can be used to compare one event to the other. Finally, disable or fork join constructs can be used to exit processes that are waiting on events. So System Verilog provides the wait order construct when the sequence in which the event occurs is important. So this construct ensures that a process is blocked until all specified events are triggered in the given order from left to right. For example, wait order E1, E2, E3. It means the process will only proceed if events E1, then E2 and finally E3 occur in that exact order. If the events trigger out of sequence, then runtime error is generated. And to handle such situations, such errors gracefully, you can pair wait order with an else to print an error message or to take any corrective action. So this feature is particularly useful in protocol checking and sequential handshakes when order matters. So this is an example to understand how wait order works. So in this example, we are declaring three events E1, E2 and E3. In the first initial block, we are triggering these events sequentially with a delay of 10 time units between each. So first we are triggering E1, then E2 and then E3. In the second initial block, we are calling wait order with the sequence E1, E2 and E3. So if the events trigger in the specified order, only then this message events executed in the specified order is displayed. And if events are triggered out of order, then this else block message will be printed. So this explains how wait order enforces event sequence and helps in detecting unexpected event timing issues. Now it's time for an assignment. So here in this assignment, you need to implement a timeout mechanism where a data sender triggers a send data event and waits for an acknowledgement event. If acknowledgement event is not received within 5 time units, then the system should trigger a timeout unit. So here I have mentioned hints also. Firstly, you can use the @ symbol to wait for the acknowledgement event. You can use fork join any construct to create concurrent threads. And finally, if the timeout condition is met, then you need to trigger the timeout unit, timeout event and display a warning. So this assignment will help you in understanding your level with event control and parallel threads in System Verilog. If you have any queries or any questions related to this topic, please send me an email or connect me via LinkedIn. Also, please subscribe to my YouTube channel for more such videos. Thank you.